Okay, thank you. Paul's talk was so good that I was willing to cede my time to him, but then he did it. No, I'm just kidding. It was perfect. And it was a perfect setup for my my lecture. Sitting here this morning really wondering how I could give a lecture in the same symposium as Jim Anderson. I've been in the same room as Jim before. We're colleagues, but it's really a special scientific opportunity to actually have a topic that brings us together. I'm an organic chemist, and I'm interested in sort of what you might call advanced organic reactivity, making complicated things. And Paul has really introduced a lot of the key topics that I need to use, concepts I need to use in my lecture. One is that synthesis of complicated molecules, and when we talk about complicated molecules, to a significant extent, those are pharmaceuticals. Not necessarily, but often pharmaceuticals. That synthesis is very inefficient. I think Paul used the number that a ton of waste is generated for every kilogram of product. You see different numbers, and of course it depends how you calculate it, but there's no question it's an enormous amount of waste. And you might think, well, it's not that big a deal because pharmaceuticals really correspond to a small amount of the total chemical product that's generated by the world. And that is true. Relatively speaking, pharmaceuticals are produced on the ton to 1,000-ton scale per year, whereas bulk chemicals and certainly petrochemicals are produced on orders of magnitude times greater scale. But the efficiencies associated with these syntheses are really dramatically different, such that depending on how you calculate it, and the numbers are ranges, of course, but depending on how you calculate it, there is about as much waste generated, chemical waste, from specialty chemical and pharmaceutical chemical synthesis. And again, Paul, I think, framed it very nicely, and I think you can ask, why is that? I think there are two explanations. One is that the molecules at issue are very complicated. Now, some of them are drawn from nature directly, from natural products, and they can be isolated and maybe manipulated with relatively little chemistry associated. So a lot of the drugs that you think of, things like tetracycline, penicillin, these are really complicated molecules, but nature gives them to us, or at least close to final form. But others are completely synthetic. And a great example of that are the HIV protease inhibitors, of which there are several on the market currently. These are 5 examples. And if you're not an organic chemist, hopefully still you can look at these and appreciate that these are complicated structures. They have not just a lot of atoms, but a lot of complexity in terms of functionality. These wedges forward and back, this is important to my lecture, these correspond to 3-dimensionality, to stereochemistry. They have what we call stereochemical complexity associated with them. And their syntheses are very difficult, involving many, many steps. And inevitably, when you have a lot of steps, you generate waste. There's another reason, I think, though, and that's, again, one that Paul touched on very nicely, and that is that really the pressure to be efficient hasn't been part of our culture, part of the organic chemistry culture. If you remember any of your sophomore organic, one of the reactions you would remember is the oxidation of alcohols with chromium reagents. And this is something we still teach. And the reason why we still teach it is because we still do it this way. Chromium reagents continue to be used to oxidize alcohols. And this is an important kind of transformation. It's something that has to be done. It is, on so many levels, a horrible process. Not just because it's inefficient in terms of the waste that's generated for the transformation that's being done. So you can calculate that in different ways, but by really a conservative analysis, you'd say that you're generating more waste than you are product. That ignores solvent and all these other elements as well. But on top of that, you're dealing with very toxic materials. You're dealing with stoichiometric generation of things that have to be disposed of, that cannot be recycled easily. This is really ugly chemistry. And so how did this develop? How did it come about? Partly it's because it really did answer the task at hand, which was, in the world in which these reagents were discovered, people didn't worry about disposal. People didn't worry about environmental issues and toxicity and things like that. Well, toxicity, yes, but people learned how to be careful as opposed to avoiding it. And this is a nice example of something that really could be fixed, because you can think about the same transformation in an extremely efficient way. You need some sort of sink to absorb the electrons, to provide electrons and to take the hydrogens off of the alcohol, ultimately to the carbonyl. And one very nice way you could imagine doing that is by reduction of O2 and generating water. So here, not only do you have much better efficiency, but of course you've got a byproduct that's a lot more friendly than in the first case. And certainly over the last several years, there's been a lot of effort directed toward discovering catalysts for this, but it's relatively recent effort compared to the long history that chemistry like this has. So I think it's just a matter of appreciating the principles that Paul laid out. Now, Paul points it out that catalysis is just part of the puzzle, so I guess this slide, I would have changed it if I had my laptop in front of me, but it's not all about catalysis. Of course, there are many other issues that are important to green chemistry, but catalysis, I'd say, is very much at the heart. Catalysis and efficiency are almost synonymous, I think, in synthesis of any complexity. So if you'll allow me, I realize that for many of you this is almost insultingly basic, but if you'll allow me to just talk about some elementary principles of catalysis. Of course, catalysis is a kinetic phenomenon. What you're doing is lowering the activation barrier to a transformation, starting materials to product. So that's conveniently represented in what we call potential energy diagrams. These are sort of simplistic ways of representing a reaction progress. You can also think about catalysis, and we do in our molecular context, as a sequence of reactions that happen to end up where they started. Okay, so a catalyst is something that does stuff but then is regenerated unchanged. Okay, and of course, along those changes is the conversion of two starting materials to a product. So these are fundamental principles and sort of guide then how you think about discovering and designing a molecule that can achieve this the lowering of the kinetic barrier to a transformation of interest. Another useful principle in thinking about catalysis is one that Linus Pauling introduced, and that is the idea that what you want to do in accelerating a reaction is essentially lower the energy of the transition state leading to the product. So a way of thinking about that is binding of a transition state and stabilizing the transition state through that kind of binding. That's sort of an abstract concept because transition states, of course, have fleeting existence. The idea of binding a transition state is a very abstract concept, but it's a useful one, certainly in terms of thinking about mechanistically what is at issue in accelerating a reaction. Okay, that's the simplest context. Almost always what you're dealing with in catalysis is not a simple acceleration, but an acceleration in the context of other possible things that can go on. So for example, if you think about methane to methanol conversion, one of the great problems of modern chemistry. Methane to methanol conversion is very, very easy. It's one of the easiest transformations you can do. The problem is that it's almost impossible to stop at methanol. Okay, so getting to partial oxidation of methane is trivial. You can do that with a match. The problem is stopping it from going to carbon dioxide. So this is a great challenge of what we'd call selective catalysis, which would be to lower the activation barrier to a desired product of an intermediate along a more complicated sequence and stopping at that intermediate. In other words, not accelerating the subsequent steps such that you can stop there. That's a terrific problem and one that defines what you would call selective catalysis. Another variant to this idea of selective catalysis is where you've got two starting materials that could go to two different products, primary products, and you want to form one instead of the other. And where, in principle, there isn't much preference, so that selectivity would be determined in the absence of a catalyst by these two barrier heights, and a selective catalyst would lower the barrier preferentially toward one relative to the other, such that you can make one selectively over the other. Okay, this all assumes kinetic control, in other words, where the reactions are not reversible, not at equilibrium. So this is really what we do in my group, and we do it in a particular context. What we do is try to design catalysts that are selective, choosing between two pathways, and the two pathways at issue are forming the two hands, mirror image related hands of a particular product, an enantiomer products. And the reason I'm sure almost all of you know is that most of the molecules of life are handed, and their handedness is directly tied to their biological activity. So it is important to control the handedness. In other words, if you're making a pharmaceutical that's handed, left to right-handed, you can't just make it as a 50-50 mixture because the two hands will probably have different biological properties. And there's, of course, a long history associated with learning about this issue, which I won't go into. Now, this is an interesting fundamental challenge because, by definition, the two hands of a molecule, the two enantiomers are equal in thermodynamic energy, and if the transition states leading to them are enantiomeric as well, in other words, left and right hand relationship, they'll also be equal in energy. So the only hope, again, of achieving selectivity, in what we call enantioselectivity, is to introduce an external chiral influence and selectively promote one pathway relative to the other such that you preferentially form one product. This is not a new concept. This idea has been around for decades. The Nobel Prize was awarded to this field several years ago to Sharpless, Noyori, and Knowles. But it's a field that continues to thrive because it's still at an early stage. It's at an early stage for many of the reasons, again, that Paul touched on. One is that we still don't know how to design catalysts very well. It's still a very, very difficult thing to do. There's still very few reactions that are done well. And there's a lot that can be learned from catalysts that do work well. And, of course, on top of all that, if we do discover these catalysts, they can solve important problems in terms of efficiency. So why is this so hard to do? One very simple reason is that the energies that you require to achieve the types of selectivity that you want, the selectivities that you require, are differences in transition state energies. Again, these are things that are hard to see, hard to calculate, hard to know with any sort of certainty. They're almost always understood by inference. And the energy differences are quite small. So to achieve what we call synthetically useful enantioselectivity, which is over 90%, which means a 19-to-1, 95-to-5 ratio of enantiomeric products, the energy difference in kilocalories per mole is quite small, in the order of 1 to 2 kcals. And even an extraordinarily selective reaction, one that gives 199-to-1 selectivity, would have only these energy differences in kcals per mole. So that's good in a sense. It means you don't need a lot of enantioselectivity to get a good reaction. The flip side is it doesn't take much. It's hard to understand these small energy differences, and it takes a lot to try to design around that. Okay, so thanks for allowing that sort of protracted tutorial on this topic. What I'm going to do initially is just show you a couple of examples of reactions that we developed a few several years ago, that I think fit this description of sort of efficiency in the context of enantioselective catalysis and did serve to solve problems. And then I'll talk about a newer set of projects, a particular new direction that I think might hold a lot of promise for future discovery. So this is a molecule I showed earlier. This is one of the HIV protease inhibitors, the one that Merck developed. And it really is a famous molecule in the circles of organic chemistry and pharmaceutical synthesis because of its complexity. It's not the biggest molecule that you'll ever see, but it stands out because of its stereochemical complexity and the fact that it is completely synthetic. There is no piece of this that comes conveniently from a natural product. One piece of this, it turns out, in red, which every piece is crucial to this molecule, but one piece that was in red, it's known as aminoindanol, is actually the starting point for the synthesis. And Merck was developing the synthesis of this drug at around the same time that my group happened to develop a reaction that allowed for epoxidation, conversion of alkenes to epoxides in an enantioselective manner. And it actually was applicable directly to the substrate of interest to them, and they were able to use it. It was one of these sort of happy coincidences where really within months of our discovering the reaction, it was applied in a significant context. And then they did a really beautiful job of what we call process chemistry to convert that epoxide to the desired amino alcohol. And this really does illustrate some nice green principles in the overall transformation, taking a coal product, indene is a coal product, to a very valuable chiral intermediate. It's 3 steps, depending on how you count, but the really key thing is the reagents are inexpensive, non-toxic, environmentally friendly, and the byproducts are few and also friendly. So this actually was interesting on a lot of levels, partly because when this happened, this was really developed in the early 90s. Nobody was talking about green chemistry. There was no issue whether this was green or not. Really, the thing that mattered here was that they needed to make as much of this compound as possible, as quickly as possible, because they needed to do the clinical trials of this molecule in an expedient way. And as it turned out, this synthesis, because of its inherent efficiency, allowed them what's called greater volumetric throughput, allowed them to make more product in a given amount of time with the equipment that they had. And that was important. That translated to actually saving lives, more people getting the drug on time. So it's interesting that these principles that, again, Paul outlined so nicely, there's an inherent sort of common sense to them, and that is that the more efficient the chemistry, the better it is. It's just that these pressures of waste minimization, efficiency, volumetric throughput really hadn't been emphasized before. And this just illustrates sort of how this was discussed. This particular example was sort of held up, again, as sort of a very practical thing. Essentially, this is an old slide that was used in Congress to describe describing this chemistry, and was really talked about in terms of economic benefits. And I show this slide only to point out how, with all this stuff, sort of sales pitch stuff, to try to explain how to Congress why it would be a good idea to fund this kind of research, there's no mention at all of green chemistry, because at that time it really wasn't considered a priority. This was sort of, the green aspect was really sort of a secondary, unanticipated benefit. Now we appreciate, I think, much better that the green component, if we had put that up front, all of these other things would have followed. This is another reaction that my group has developed, and it's another example sort of efficiency in a significant way. This is a method that is very simple. It takes an epoxide that's racemic, meaning that there are two enantiomers, left and right hands, in this mixture, and with water as a reagent, takes one of the two enantiomers to a product. It opens the epoxide to this dial, leaving the other one behind. And it does so with almost perfect selectivity, such that both the product and the starting material can be isolated in close to pure form. Now, why do I show this example? Partly because it solved the problem. This is a useful chiral building block that was being synthesized at the time from lactic acid in several steps with a lot of waste generation. And inefficiently, this was a lot more efficient way of doing this. But it really does sort of have extraordinary green properties to it. Even though it's a resolution, even though you're making a byproduct, okay, that byproduct is very valuable in and of itself. The separation is very easy, very low energy. The volumetric throughput is perfect because these reactions are done in the absence of solvent. All these elements that allow for a low-cost process and a environmentally friendly process. On top of that, the catalyst itself involves a non-toxic metal, relatively simple molecule, and one that can be recycled. Now, we did a lot of work on this reaction to try to understand how it goes, and I won't tell you that story except to say that, oops, doesn't like that slide, there, that we did glean some real insight into the mechanism of this reaction and learned that it involves two metals coming together in a cooperative way, one to activate the epoxide, which is shown here, and the other to activate the water that's shown here. That insight allowed us to design better catalysts by linking them together in specific ways that were extraordinarily efficient, such that we can now, instead of using, as we do here, on the order of a tenth of a mole percent, so 1 part per thousand or 2 parts per thousand catalyst, with the newer catalysts we could use parts per million or subparts per million catalyst. So not only, again, is it an efficient process, but very efficient from the catalyst point of view. And it could be applied to a number of different products. And again, I realize for this audience, a lot of this is not that useful information, except I'm trying to impart on you the notion that this is a general catalyst, something that can be used to make a lot of different products. The ones that I've boxed are ones that have been carried out in a commercial context. There's, as I showed you in the initial example, there's a connection then to pharmaceutical synthesis. This particular one is manufactured on over 50-ton scale per year by this company Daiso in Japan, and this is the plant that does it. And again, the advantage to this chemistry is that it really produces very, very little waste because no solvents are used. The products and the product and byproduct are both valuable, and the catalyst is recycled. Okay, I'm going to spend the rest of this lecture talking about a newer direction in the group, and it's one that's as fundamental as it gets when it comes to catalysis. If you remember anything from catalysis in terms of enzymatic chemistry or zeolite chemistry or things like that, the catalyst that you most often see is the simplest possible elementary catalyst, and that is H+, the proton. The proton is an extraordinarily effective catalyst, and that is because when associated to all sorts of different kinds of molecules, including classic organic molecules like imines, carbonyl compounds, epoxides, or alkenes, the proton in association with those compounds generates a highly reactive intermediate and increases the reactivity in a very significant way. In each of these cases, to make what we call a very electrophilic species, something that wants desperately to get electrons to react with a nucleophile, and an enormous amount of organic chemistry follows from this, from proton activation. And the proton is good about then coming back off to recycle, in other words, to be used in a catalytic way after it's done its work. So a question that we've been asking ourselves over the past several years is, can we do selective chemistry with the proton? Can we, protons are known to catalyze reactions, to accelerate reactions. Can we sort of harness that reactivity in a selectivity context, and ideally in an anti-selectivity context? And to make a long story short, that's a very hard thing to think about doing because of the very reactive nature of these species and the fact that they really don't have anything to hold on to. They normally, when you think of a catalyst binding to something, you think in terms of electrons being available to bind to it. These things lack electrons. They're electrophilic. Okay, so how do you bind, how do you activate something that's as reactive as these species? And the answer didn't come to us immediately, but the answer, as it turns out, is very obvious in retrospect, and that is, for every cation, there's a conjugate base. There's an anion associated with that to balance the charge. And if you bind that anion with a chiral catalyst, and you can induce communication between this ion pair in appropriate ways, you could hope to impart selectivity on reactions of these reactive species. So the problem then becomes one of binding anions, and if that's a doable proposition. And it turns out that there's been a fair amount of work in the molecular recognition field around anion binding. And one of the more interesting results of that is that hydrogen bond donors of various types, and in particular ureas and thioureas, are very good at anion binders. And when I say very good, I mean that they can bind anions. They really have almost no basicity associated, no Bronsted basicity, things that don't really want a proton associated. Chloride is a very weakly basic compound. HCl is a very strong acid. Yet this molecule, this urea derivative, binds Cl- very, very efficiently, even in polar solvents. And people have recognized this for years, and based on that, people have designed sort of receptors for anions based on the thiourea, that's a sulfur flanked by two nitrogens, this functional group, or urea framework, with particular shapes associated with them such that they could bind one anion, let's say in the presence of another anion. And these molecules do things like bind halides or sulfates, sulfonates, phosphonates, all sorts of different anions that have very poor basicity. So the idea that we have developed is one where we might be able to do a selective reaction or a selective class of reactions. Let's say, imagine adding a nucleophile to a multiple bond. To do so enantioselectively, meaning that we're taking an achiral, not handed starting material to a chiral product, to do that in an enantioselective way with a chiral catalyst, with the agency of a strong acid to activate this substrate, and a chiral catalyst then to essentially activate the acid or associate with the acid as its conjugate base, as its anion, and where enantioselectivity may be then induced through this ion pair intermediate. Okay, so it's a complicated idea, but hopefully one that you see in this catalytic cycle. So as I've drawn it here, you can imagine the acid being activated by the chiral catalyst, making it more acidic to protonate the substrate. You could also imagine that this acid protonating the substrate directly and the catalyst binding to that salt, and then in addition to this substrate. So what I'm going to do is show you an example of this because we've reduced this to practice, and I hope that it's a first example of what will turn out to be a general type of catalytic reaction, selective catalytic reaction. So the reaction we've studied, as you know, organic reactions have thousands of different names. I've even got a name reaction. It doesn't take much. So Povarov has a name reaction, and it's this one shown here. It's a variation of the Diels-Alder reaction where you have a cyclization between an electron-rich alkene and an aryl-substituted imine. Okay, and this is a reaction that's catalyzed by strong acids. I'll use the word strong acid or superacid. What I mean by that is something that's essentially that will protonate water quantitatively when it's dissolved in water. Something that's got a pKa in the negative range, okay, as triflic acid does. It's a very strong acid. The kinetic behavior of this reaction is consistent with the substrate being completely protonated before, as in the resting state. So this catalyst protonates the amine to the aminimine, and then what you have is a rate-determining reaction between this olefin and the iminium salt to make this, and then the proton comes off of the aromatic ring, and you get the product. Now, weak acids, such as ureas and thioureas, do not catalyze this reaction. Not surprisingly, ureas and thioureas are very weakly acidic. They have pKa's around 20, so 20 orders of magnitude times less acidic than molecules like this. But the remarkable thing in the discovery is that if you combine triflic acid with this chiral catalyst, this chiral urea derivative, you induce the desired reaction. You change the stereochemical relationship. I won't go into that in detail, but the bottom line, the important point, is that you could turn on a very highly enantioselective pathway that leads to this product. It is almost a pure enantiomer. So somehow this catalyst is working together with this catalyst that doesn't need help, that does it all by itself, but doing so to turn on an enantioselective pathway. Okay, so it just turns out that this particular reaction is of interest because this framework that we're making here shows up in all sorts of different natural products that have interesting biological activity. And I won't go into detail there, but just to emphasize that there's a reason to want to do this reaction. These kinds of building blocks and targets are quite valuable and of interest, and there hasn't been a good way to make them. So what we've done is to explore this as a methodology. One of the things that we do in my group then is to try to discover catalysts, optimize it, work out its parameters, and then try to show its scope, to show that it's as general as possible across a range of products. And again, I don't hope at all that you will read all of this or absorb it, but just for effect, to see that there are a lot of different products here, and in each case, the product is formed in reasonably good yields, but more important, in very good enantioselectivities. Okay? And this is true for this class of alkenes, these dihydroperols. It's also true for these vinyl lactams. In this case, the reactions are really perfect. There's really only one product generated in very high enantioselectivity, and the yields, which are isolated yields, are close to the theoretical maximum. Okay, so again, just to drive home that it's a general reaction and it's synthetically useful. But what I'd like to end with is how does this work, and what does it teach us, and how might we use that? So the question is, fundamentally, I mean, I've sort of given you the answer, how we think these catalysts might work, but we really weren't certain. The idea, or the question is, how does this molecule that's a simple thiourea, interact with a highly reactive iminium triflate salt? And we know that that's what we're dealing with, an iminium triflate. Well, there are nice Nmr experiments that can be done to address the degree of ion separation in this ion pair. And it turns out that if you separate these ions, either by introducing a more polar medium or by sequestering this anion, the chemical shift of this proton goes what we call upfield to a smaller number. And that's what we see with this simple thiourea derivative. This is not a chiral molecule. It's a simple thiourea. You see what's actually a sizable shift in the NMR signal for that proton. When we use the chiral catalyst that works well in our reaction, we see an opposite effect. We see a large shift in the opposite direction, in a downfield sense. What that's telling us is that this proton in this iminium ion is becoming more deshielded, which means that there's something associating with it. It's not that it's becoming less associated, it's becoming more associated. And what we've been able to establish through these NMR experiments and through computational studies is a secondary interaction, one where you have a primary interaction, the thiourea is binding the anion, as we had hoped, but then a secondary interaction where this ancillary functionality, what's called the sulfonamide, is interacting with this proton, this formula proton of the iminium ion, okay, such that you have now a dual kind of interaction, an ion pair interaction as well as a hydrogen bond interaction. And it's the combination of those two that allows the enantioselectivity. As Paul pointed out, using weak non-covalent interactions to achieve catalysis is something that really hasn't been done very much. Enzymes do it as a principle, but in terms of small molecule catalysts, people have tended to rely on strong covalent interactions. These are very weak interactions, but by working in concert, they allow for a positioning of the substrate. And now what you have here is, again, a picture of this now in line drawing and in a ball and stick drawing, where you've got the sulfonate associated with the iminium ion, primarily in an electrostatic manner, and then a hydrogen bond between the sulfonamide and this hydrogen. That combination has the effect of blocking one face of the substrate and leaving the other exposed. Okay, and that's what you want for an enantioselective reaction. You want to block one side and leave the other available to react. So there's interesting questions associated with, well, is this catalyst, by doing this, is it making this iminium ion less or more reactive? We've been able to show that it's actually making it less reactive. But because we're using a catalytic amount of the acid and of the chiral catalyst, all of the iminium ion that's generated is bound to the chiral catalyst as well. In other words, we're always in this state. Even though this is more reactive than this towards substrate, you don't have any of this in the free state because this equilibrium constant, the binding of the chiral catalyst to this iminium salt is very high. That's a subtle point. The main issue is that we've got catalysts associating with the anion, a secondary interaction with the iminium ion. Again, there's more detail here than is probably appropriate. Maybe I'll just go to the bottom line. The question is, well, what is important in the actual reaction? What I've shown you here is how it binds to the catalyst. What matters is how it reacts with this substrate or with this type of substrate. And the questions that we ask are, well, is it a stepwise or is it a concerted reaction? Is the first step or the second step determining the selectivity? Just to jump to the end, by using sort of classical tools of physical organic chemistry, what we've been able to show, or at least provide evidence for, is that it is in fact a concerted, what we call a concerted asynchronous reaction, meaning that all the bonds are being formed at the same time, but not simultaneously, meaning that not to the same extent in the key transition state. As a result of that, what we know is that the selectivity of the reaction is determined in the addition of this to that. So that's what we need to study. Again, what I'm showing you is really sort of how the problem evolves. How do you design a catalyst? Well, first step is by understanding catalysts that work. If we can understand this catalyst at a high level of detail, we can use these principles for other things. And again, all the information here is designed to show you that we can now address this question, knowing that this is the determining event. What controls the selectivity? We can study this computationally using different kinds of tools. And one of the things that we've been able to do using sort of standard computational methods is to come up with a picture for the selectivity determining transition state that corresponds to the observed product. So the bottom line is a reaction that really goes by a fundamentally new mechanism that I think we understand in a very, very deep way. So that's really just an example of the kinds of reactions that one could think about doing. What I won't go into any detail, but hopefully just to impress on you that this is a general concept. Using this idea of hydrogen bonding to an anion or to an electrophile to stabilize a negative charge, either in an anion, in an ion pair, or to developing negative charge in an electrophile as a nucleophile adds to it. And then using some sort of an ancillary functionality, something that can direct the nucleophile or activate the nucleophile in the addition step. We can do all sorts of different things, all sorts of combinations. These are the different examples of different types of products that we can generate around this simple idea. And again, I don't hope for you to see these in any sort of detail, except to maybe appreciate that they're different looking kinds of compounds, very different, all of them chiral, most of them are what we call bifunctional, meaning that they have multiple handles to do subsequent chemistry. And these are things that are valuable for synthesis of complex molecules. So what do we hope to do with this idea in the future? I think that this is applicable to all sorts of different things that I think may be important in making reactions more efficient. One of the great problems in organic chemistry and in catalysis right now is a problem called hydroamination, addition of an amine across a double bond. And it's represented by the idea of taking ammonia and an alkene and bringing them together, adding an NH bond of ammonia to an alkene. That's a very tough problem and a very important problem. Now, there's a variant to that that you can think about using a strong acid catalyst, as shown here. And the idea would be to use a strong acid to activate the alkene, generate a carbocation, stabilizing the anion, and then use a nitrogen-based nucleophile, like acetonitrile, a non-toxic solvent, that could trap that carbocation, ultimately leading to this amide. So this is a real possibility now because we know that we can do this kind of anion binding directed asymmetric catalysis. And in fact, we've got good results in this direction. You can also think about much more complicated things like really mimicking the types of chemistry that nature does well. Nature takes polyolefins. W.S. Johnson was a pioneer at Stanford in doing this kind of chemistry in a synthetic context, taking polyolefins and doing extraordinary tandem cyclizations to generate polycyclic frameworks. This is, in fact, the chemistry that's at the heart of the steroid biosynthesis and the cyclization of oxidosqualene to this tetracycle. This is a transformation that's done enzymatically. A lot is known about the enzyme, and the basic idea is an acid to activate the electrophilic functional group. And then, remarkably, what the enzyme does is use weak secondary interactions, mostly it's hydrophobic interactions, to surround all of these functional groups that are reacting and orient them and stabilize charge and position them just right such that they cyclize in a particular way. This is something that looked impossibly complicated, impossibly difficult, and sort of belonged in the realm of the magic of enzymes until recently. But now it's something that one can think about doing with a small molecule, really just by taking an acid and then a chiral catalyst that could, in principle, then just have just the right minimal number of interactions to stabilize and orient these things. So that's the kind of direction that I can imagine this going. Really using catalysis to do synthesis in a wide range of contexts. So with that, I'd like to end. I hope I didn't go over. I'd like to thank the Dreyfus Foundation for funding almost all the research that I talked about in this lecture. So this project has been the work primarily of Hao Xu, a postdoc in my lab who's got a Dreyfus Fellowship. He's in a very productive collaboration with Stefan Sund, an extraordinary physical organic chemist in my group. So I'm grateful certainly to Hao and to Stefan and to the Dreyfus Foundation for supporting this work and for inviting me here. Thank you very much.